What if the universe you see is only a sliver of the truth? What if the starlight that has guided us for millennia, the celestial fire that has fueled our myths and our science, is merely the froth on a deep, dark and invisible ocean? This is not a philosophical riddle. It is the central confounding and exhilarating mystery of modern cosmology. We are living in a ghost universe. For every star that burns, for every galaxy that wheels in the cosmic night, for every particle of dust and every atom in your own body, there is something else, something that outweighs it all 5 times over. A pervasive unseen substance that provides the very architecture for existence, a silent partner to reality that holds the cosmos in its grip. It has a name that speaks to its profound enigma, dark matter. It is the universe's ultimate magic trick, a grand illusion played out on a stage of 13.8 billion light-years. And we, the audience, have only just realised the stage itself is part of the act. This is not a story about the absence of light. It is the story of a presence that emits no light at all, a substance so fundamentally different from our own that it flows through walls, through planets, through us as effortlessly as a phantom passing through a castle door. It feels nothing we can feel, it touches nothing we can touch, and yet its influence is absolute. Its power is felt in the inexorable pull of gravity. It is the cosmic anchor holding our Milky Way together, preventing its hundreds of billions of stars from spinning off into the void. Imagine a carousel spinning with impossible speed. Any child sitting on its edge would be flung outwards, their grip broken by the sheer velocity. In the 1970s, astronomers like Vera Rubin looked at distant galaxies and saw exactly this cosmic carousel. The stars on their outer edges were moving too fast, far too fast. According to every law of physics, we held dear the visible matter. The stars, the gas, the glowing nebulae was simply not enough to keep them in orbit. These majestic spiral galaxies should have torn themselves apart, their brilliant stars scattered like celestial dust in the wind, but they weren't. They held together serene and stable, defying the known laws of gravity. The conclusion was as inescapable as it was terrifying. There had to be something else there, a vast invisible halo of mass, a gravitational ghost cradling these islands of light and holding them in a firm, unseen embrace. This was not the first hint of the universe's secret. Decades earlier, the brilliant and irascible Fritz Zwicky had observed the Coma cluster of galaxies, a sprawling city of 1,000 star systems. He saw them buzzing around each other like angry bees, moving at speeds that suggested the cluster contained hundreds of times more mass than could be accounted for by its luminous galaxies. He called this missing mass Dunkel Materie, dark matter. His ideas were dismissed for nearly half a century, the ramblings of an eccentric genius. But the universe, it turns out, is far more eccentric than we ever dared to imagine. The evidence continued to mount, becoming an avalanche. We saw its effects in the way light from distant objects is bent magnified and distorted as it passes through unseen concentrations of mass, a phenomenon called gravitational lensing. Dark matter was acting like a cosmic telescope, its gravity warping the very fabric of space-time, revealing its presence through the strange, warped images of the universe behind it. We saw its imprint on the most ancient light in the universe, the faint afterglow of the Big Bang, the cosmic microwave background. The patterns of hot and cold spots in this primordial light could only be explained if the early universe was dominated by a strange non-interacting substance that could clump together under gravity long before normal matter could. This dark matter was the seed. It was the invisible scaffolding upon which everything we know was built. It formed the first gravitational wells, the cosmic potholes into which hydrogen and helium gas would later fall, igniting the first stars and assembling the first galaxies. Without dark matter, there would be no cosmic web, that vast filamentous network of galaxy clusters and superclusters that stretches across billions of light years. There would be no structure, no galaxies, no stars, no us. We are here because the dark was there first, and yet we have never ever touched it. For generations we have built our most sophisticated experiments in the deepest, quietest places on Earth. Halls of impossibly pure materials shielded by kilometers of solid rock, designed to listen for the faintest whisper of a dark matter particle as it passes through our world and collides just once with an atom of our own. But the silence from these experiments has been deafening. The ghost has eluded every trap we've set. This profound failure has forced us to confront a humbling truth. Perhaps we have been looking in the wrong way. Perhaps the secret to dark matter isn't hidden in the quiet darkness of a mine, but in the brilliant, violent light of the universe's creation. Humanity has always built bigger eyes to gaze upon the heavens. From Galileo's first crude telescope to the gleaming observatories that dot our planet's mountaintops, each new instrument has peeled back another layer of reality, revealing a cosmos more complex and more magnificent than the one before it. The Hubble Space Telescope, our loyal sentinel for over 3 decades, showed us a universe teeming with billions of galaxies. It pushed our vision back to a time when the cosmos was young. But even Hubble has its limits. Its vision, powerful as it is, cannot pierce the veil of the true cosmic dawn. It cannot see the very first lights to ever switch on in the universe. To do that, we needed to build a different kind of eye, a machine not just of glass and steel, but of ambition and gold. A technological marvel designed to capture the faintest, most ancient photon's light that has been travelling towards us since the dawn of time, stretched by the expansion of the universe into the infrared spectrum invisible to the human eye. We needed to build a time machine, and so we did. The James Webb Space Telescope, a dream articulated over a generation brought to life by the ingenuity of thousands of minds from around the world. Its 18 hexagonal gold-plated mirrors, a breathtaking honeycomb designed to unfold with balletic precision 1,000,000 miles from Earth. Its tennis court-sized sun shield, a technological parasol of 5 gossamer-thin layers, engineered to keep the telescope in a perpetual cryogenic shadow, colder than any freezer on Earth. This magnificent instrument was not sent on its lonely journey merely to take more beautiful pictures of the cosmos. It was launched on a singular, audacious quest to travel back to the beginning, to witness the end of the cosmic dark ages, that period after the Big Bang, when the universe was filled with a neutral fog of hydrogen before the first star had ever ignited. JWST was built to find those first tentative sparks of creation, the birth cries of the very first stars, the chaotic assembly of the first infant galaxies. It is the ultimate origin story machine. And here in the nursery of the cosmos, the story of light and darkness may finally converge. The central thesis, the revolutionary idea now electrifying the world of astrophysics, is that JWST has not just fulfilled its primary mission. In peering back 13.5 billion years, it may have inadvertently stumbled upon the ghost in the machine. It may have found the first tantalizingly direct evidence of dark matter's pervasive influence, not through what it is, but through what it does to the very first things that shine. The theory suggests that in the extreme conditions of the early universe, dark matter wasn't entirely silent. There may have been a way for it to interact with itself, a process of annihilation that would produce a unique and unexpected kind of heat. Not the light of fusion from a normal star, but a steady ethereal glow, a dark matter burn, powering a new and bizarre type of celestial object. A dark star fueled not by hydrogen, but by the unseen majority of the universe. And as JWST focused its golden eye on galaxies at the edge of time, it began to see things that shouldn't be there. Galaxies that were too bright, too massive, too well formed for their tender age. They seemed to have grown up too fast, like infants born with the bodies of adults. Our standard models of cosmology, the very pillars of our understanding, struggle to explain their existence. They are anomalies, paradoxes shining out from the dawn of time, unless something else was at play. Unless these first galaxies were not just built upon an invisible scaffold of dark matter, but were actively being shaped and illuminated by it. What if these impossibly bright early galaxies are not what they seem? What if JWST is seeing the signature of dark matter's presence written in the light of the first stars themselves? The implications are staggering, forcing us to re-evaluate everything we thought we knew about the universe's first billion years. We stand at a precipice of discovery, a moment of profound change. The invisible scaffolding of the cosmos is no longer content to remain in the shadows. It is beginning to reveal itself not in our quiet laboratories deep underground, but in the most distant, most ancient light our eyes have ever seen. The ghost is finally beginning to talk, and our journey now is to learn its language. What if the universe we see is only a sliver of the truth? What if the grand celestial dance of galaxies, stars and planets, a spectacle of light and gravity playing out across billions of years, is merely a luminous frost on a window, hiding a vast, dark and unseen landscape? This is not a question of philosophy, but of physics. It is a profound and unsettling puzzle that has haunted astronomers for nearly a century, a cosmic detective story whose first clue was not found in a brilliant flash of discovery, but in a quiet, disturbing anomaly, a deep cosmic dissonance, a sense that the universe was simply not adding up. Our journey into this great unknown begins not in the space age but in the 1930s, an era when the cosmos itself seemed to be expanding in our consciousness. Edwin Hubble had only recently proven that the faint smudges we called nebulae were in fact entire island universes, galaxies like our own, scattered across an impossibly vast void. The scale of existence had been redrawn, and at the astronomical frontier at the windswept summit of Mount Wilson in California, a new generation of cosmic cartographers pointed their colossal telescopes towards these newfound realms, eager to chart their motions and weigh their souls. Among them was a man as turbulent and brilliant as the exploding stars he studied, Fritz Zwicky, a Swiss-born astronomer at Caltech. Zwicky was a visionary, a lone wolf with a formidable intellect and a personality that could charitably be described as abrasive. He famously referred to his colleagues as spherical bastards, because he claimed they were bastards no matter which way you looked at them. But this combative nature was fused with a breathtakingly creative mind, one that saw connections others missed to mind unbound by convention. And in 1933, as he turned his attention to the magnificent Coma cluster, a sprawling city of over 1,000 galaxies, some 320 million light-years away, his intuition detected something profoundly wrong. He wasn't just observing these galaxies, he was putting them on a scale, a gravitational scale. The method was in principle straightforward. Just as you can calculate the Sun's mass by the speed and orbit of the Earth, Zwicky could estimate the total mass of the Coma cluster by observing the frantic motions of its member galaxies. He watched them swarm and orbit a common gravitational centre, like a hive of celestial bees. The faster they were moving, the more total mass there had to be in the cluster, its immense gravity acting as a cosmic anchor preventing the whole glittering assembly from flying apart into the void. He meticulously calculated their velocities, their orbital speeds within the cluster's maelstrom. The numbers that came back were staggering. The galaxies were moving with astonishing speed, careening through the cluster at thousands of kilometers per second, far, far too fast. This is where the dissonance began, the first whisper of the phantom. Zwicky then undertook a second independent calculation. He painstakingly estimated the cluster's mass based on what he could actually see, the combined light from all of its 1,000+ galaxies. He counted the stars, estimated their mass, and added it all up. This gave him the total visible mass, the luminous matter of the cluster. When he placed the two results side by side, they were not just different. They were violently, irreconcilably at odds. The gravity required to hold the speeding galaxies in place was monstrously larger than the gravity that all the visible stars could possibly generate. It was like watching a child on a merry-go-round spinning at the speed of a jet turbine yet remaining perfectly seated. Some unseen force, some colossal invisible grip had to be at work. By Zwicky's own calculations, the Coma cluster contained at least 400 times more mass than could be accounted for by its starlight. Something else was there. Something massive. Something dark. He gave it a name, a simple, direct and haunting name, Dunkelmaterie. Dark matter. It was a revolutionary, almost heretical proposition. That the vast majority of the substance of the universe was completely invisible to us, its presence betrayed only by the subtle yet unyielding tug of its gravity. For Zwicky it was a logical necessity, a ghost the equations demanded. But for the wider astronomical community it was a step too far. His data was questioned. His methods were scrutinized. His abrasive personality certainly didn't help win him any converts. The discrepancy, they argued, could be due to errors in distance measurements, or perhaps some unknown physics we had yet to understand. For decades, Zwicky's astonishing discovery, this first glimpse into the universe's invisible architecture, was relegated to the footnotes of cosmology. A curious unsolved puzzle, but not a crisis. The ghost remained in the machine, but most chose to simply ignore it. The mystery lay dormant, a sleeping giant in the heart of astrophysics for nearly 40 years. It would take a different kind of observer with a different tool and a profoundly different temperament to awaken it. Her name was Vera Rubin. Working in the 1960s and 70s, Rubin was a meticulous, patient and deeply thoughtful astronomer, a pioneer who navigated the challenging, often exclusionary male-dominated world of her field with quiet determination and grace. She wasn't looking for a cosmic ghost. She was interested in the dynamics of individual galaxies, the grand spinning pinwheels of stars that are our cosmic home. Her chosen subject was our nearest major neighbour, the Andromeda Galaxy. Using the advanced spectrographs at Kitt Peak and Lowell observatories, Rubin and her colleague Kent Ford developed a technique of unprecedented precision. They could measure the speed of stars orbiting the galactic centre at various distances, from the glowing crowded core to the faint lonely outer edges. Everyone knew what she should find. The laws of gravity established by Newton and refined by Einstein were clear and unambiguous. Just as in our own solar system, where the inner planets like Mercury race around the Sun, while the distant planets like Neptune crawl along in their orbits, the bulk of a galaxy's mass should be concentrated where the stars are brightest in the centre. Therefore, stars orbiting far out in the galactic suburbs, far from the central gravitational anchor, should be moving much more slowly than the stars in the dense inner regions. Her measurements were expected to produce what astronomers call a Keplerian decline, a graph of stellar velocity versus distance from the centre should show a sharp peak for the inner stars, and then a steady predictable drop-off for the stars further out. That was the confident prediction. It was simple, elegant, and obvious, and it was completely, utterly wrong. Night after night, as the data came in, a startling and impossible picture emerged. The stars in the inner part of Andromeda were indeed moving quickly, just as expected. But as Rubin and Ford measured the velocities of stars further and further out, the speeds did not drop. They held firm. Stars on the galaxy's farthest visible fringe, tens of thousands of light years from the core, were orbiting just as fast as stars much closer in. The galaxy rotation curve, the graph of these velocities, was not a steep decline. It was stubbornly, unnervingly flat. It was as if Neptune were orbiting the Sun at the same blistering speed as Mercury. This was not a subtle error. It was a flagrant violation of the laws of physics as they were understood. It was cosmic rebellion on a galactic scale. At first, Rubin was skeptical of her own findings. She rechecked her equipment, her calculations, her assumptions. The result was unyielding. There was no mistake. The only way to explain this bizarre flat rotation curve was to accept that the galaxy was not what it appeared to be. The visible disk of stars, the glorious spiral we can photograph, was just a small luminous component embedded within a much, much larger structure. A vast spherical halo of invisible matter extending far beyond the edge of the starlight had to be enveloping the entire galaxy. Its gravitational influence was everywhere, holding those fast-moving outer stars in their orbits, preventing them from being flung into intergalactic space. Andromeda was not just a disk of stars, it was a gravitational island whose true mass and size were dominated by an unseen component. What Zwicky had seen in a chaotic cluster of 1,000 galaxies, Vera Rubin now saw with irrefutable clarity in the calm, stately rotation of a single one. She didn't stop with Andromeda. Driven by a need for certainty, she turned her instruments to other galaxies, dozens of them of all shapes and sizes. And everywhere she looked, she found the same ghostly signature. Spiral after spiral, galaxy after galaxy, the story was the same flat rotation curves. The luminous matter was a mere afterthought. The universe we could see was being puppeteered by a universe we could not. Her evidence was so comprehensive, so meticulously gathered, so powerfully consistent, that it could no longer be ignored. Fritz Zwicky's forgotten idea, his dunkle materie, was resurrected not as a fringe theory, but as a central, unavoidable crisis in our understanding of the cosmos. The problem of missing mass was now firmly established. There was simply not enough visible matter stars, gas and dust to provide the gravity needed to hold galaxies and clusters of galaxies together. This revelation triggered a paradigm shift in cosmology, forcing scientists to construct a new model of the universe, one that embraced this vast invisible reality. The question was no longer if dark matter existed, but what it could possibly be. And the process of elimination began almost immediately. Could it be just ordinary matter that's hard to see? Things like cold gas, faint brown dwarfs, or rogue planets wandering in the dark. These were dubbed machos for massive astrophysical compact halo objects. Intensive searches were launched looking for the telltale gravitational lensing events that would occur if such an object passed in front of a distant star. Some were found, but their numbers were far too small. The math showed that there simply weren't enough of these dim conventional objects to account for the colossal gravitational deficit. The answer had to be more exotic. Could it be a sea of stray black holes, the remnants of the universe's first stars? While they are dark and massive, their formation and distribution don't quite fit the observational evidence. Furthermore, the delicate balance of elements forged in the Big Bang imposes stricter limits on how much normal matter, made of protons and neutrons like us, can exist in the universe. And that number falls hopelessly short of what's needed. The ghost, it seemed, was not made of the same stuff as us. It had to be something new, something entirely outside our standard model of particle physics, something non-baryonic. And so the modern conception of dark matter began to take shape. It is a substance fundamentally different from anything we have ever known. We can infer its properties from its gravitational behavior, painting a portrait of a phantom. First, it is dark, not just dim, but utterly transparent. It does not emit, absorb, or reflect any form of light or electromagnetic radiation. It is a perfect stealth material on a cosmic scale. If you were holding a clump of it in your hand, it would be completely invisible. Your hand would feel its weight, but your eyes would see right through it. Second, it is cold. Not in the sense of temperature, but in that its particles move slowly compared to the speed of light. This is a crucial property because cold, dark matter clumps together easily under gravity, providing the necessary seeds for cosmic structure to grow. Hot, dark matter, like fast-moving neutrinos, would simply zip around too quickly, smoothing out any clumps before they could form galaxies. Finally, and most profoundly, it is collisionless. Its particles barely interact with each other or with us. They are ethereal, passing through normal matter like ghosts through a wall. Billions of dark matter particles are likely streaming through your body through the Earth itself every single second, and we feel absolutely nothing. Their only significant interaction is the one force they cannot escape: gravity. With these properties, dark matter became the indispensable ingredient in our modern understanding of the cosmos, the lambda cold dark matter model. In this new cosmology, dark matter isn't just a mysterious add-on, it is the primary architect of the universe. It is the invisible scaffolding upon which everything we see is built. In the aftermath of the Big Bang, the universe was an almost perfectly smooth, hot, dense soup of particles. But there were tiny quantum fluctuations in its density, minuscule regions that were slightly denser than others. In the ocean of a normal radiant matter, pressure fought against gravity, making it difficult for structures to collapse and grow. But dark matter, feeling only the pull of its own gravity, and nothing else, was free to begin collapsing immediately. It formed vast, invisible pools of gravity, enormous halos that grew larger and larger. These halos created the deep gravitational wells, the cosmic potholes into which normal matter could then fall. Over hundreds of millions of years, hydrogen and helium gas were inexorably drawn into the centers of these dark matter halos, where they finally became dense enough to ignite, giving birth to the first stars and galaxies. The universe we see today, this spectacular cosmic web of galactic superclusters and filaments stretching across billions of light years, is a direct consequence of this process. The luminous galaxies are like shimmering dewdrops that have condensed onto a vast invisible spider's web of dark matter. The web itself is the true underlying structure of the cosmos. We live in its illuminated intersections. The numbers are as humbling as the concept itself. When we tally up the universe's total mass and energy budget, the results are a stark testament to the scale of our ignorance. Everything we can see and touch, Every star, every galaxy, every planet, every atom, all the stuff we call matter, accounts for a paltry 5% of the cosmos. Roughly 27% is this strange, invisible dark matter, the gravitational backbone of the universe. The remaining 68%, an even more mysterious entity called dark energy, is driving the accelerating expansion of space itself. We are, it turns out, strangers in a universe whose fundamental nature remains almost entirely unknown to us. We have charted the ghost's influence with breathtaking precision. We see its effects in the spinning of galaxies, in the motions of clusters, in the way light from distant objects is bent and distorted as it passes through the unseen gravitational fields of dark matter halos. The indirect evidence is overwhelming the theory elegant and powerful. Yet a profound nagging unease has settled over the field of physics. For all its explanatory power, we have a theory with a gaping hole at its centre. We have given the ghost a name, but we have never seen its face. For decades we have built fantastically sensitive experiments, deep underground, shielded from cosmic rays designed to catch the barest whisper of a dark matter particle bumping into an atom of normal matter. And after all this time, all this effort, the result has been an unnerving, profound silence. Every experiment has come up empty. The ghost has refused to show itself. This long, fruitless search has led some to wonder if we're on the wrong path entirely. Could it be that there is no dark matter particle, that our theory of gravity itself is flawed on the largest scales? A quiet crisis has been brewing in the heart of cosmology. The elegant solution to the problem of missing mass has become its own kind of mystery. A perfect theory with no direct proof. To solve it, we need more than a new experiment. We need a new way of seeing. We need a machine that can look back in time to the cosmic dawn, to the era when the first galaxies were just beginning to condense within those primordial halos of darkness. We need an eye so powerful it can witness the very moment of creation to see if the ghost has left its fingerprints on the universe's earlier structures. And now, finally, we have it. The triumphant discovery of this gravitational ghost had ignited a firestorm in the scientific world. Suddenly we had a map of the invisible, a blueprint for a substance that outweighed everything we could see by more than 5 to 1. The cosmic inventory was rewritten overnight, and a grand hunt began. Not with telescopes aimed at the sky, but with instruments aimed at the very fabric of reality itself. The prevailing theory, elegant and powerfully predictive, was that dark matter consisted of new undiscovered particles. They were dubbed WIMPs, weakly interacting massive particles. The name itself was a masterpiece of understatement, a clinical description for the most elusive quarry in the history of science. These were not particles like the familiar protons or electrons that build your world. WIMPs, theorists proposed, were relics from the Big Bang's first ferocious second. They were heavy, slow-moving and fantastically antisocial, passing through ordinary matter as if it were nothing more than empty space. Billions of them, the model suggested, are streaming through your body, through the Earth, through the Sun, every single moment, utterly oblivious to our existence. They are the silent, unseen wind of the cosmos. And for a generation of physicists, the challenge was intoxicating. The Nobel Prize and a fundamentally new understanding of the universe awaited whoever could catch one. It seemed for a brief heady moment that we were on the verge of success. Particle physics had provided a candidate that fit the bill perfectly, a particle predicted by theories like supersymmetry. It was an idea so beautiful, so neat, it felt like it had to be true. This WIMP miracle, as it came to be known, promised that a particle with the right properties to be dark matter would also naturally solve other deep problems in physics. The universe, it seemed, was offering us a 2-for-1 deal. All we had to do was build a trap. But how do you catch a ghost? How do you build a net for a particle so phantom-like that an entire light-year of solid lead would fail to stop it? The answer was a paradox to find the most abundant thing in the universe. We had to build the quietest, cleanest, most isolated places on Earth. We had to descend, leaving the light of the stars behind, burrowing deep into the planet's crust. We had to go into the dark to find the dark. The primary enemy in this hunt was noise. Not sound, but the constant shower of cosmic rays and other energetic particles that rain down on our planet's surface. This relentless particle static would create a blizzard of false signals, hopelessly drowning out the whisper-faint signature of a single WIMP. To escape this cosmic storm, physicists became miners transforming old gold mines, road tunnels, and purpose-built caverns into modern-day cathedrals of science. Journey with us a mile deep beneath the Black Hills of South Dakota to the Sanford Underground Research Facility, former home of the Homestake Gold Mine. Here in a chamber carved from ancient rock, shielded by the sheer bulk of a planet, sits an experiment called LUX, the Large Underground Xenon Detector, and its even more sensitive successor LZ. Or travel to Italy to the Laboratory Nazionale del Gran Sasso, nestled in the heart of a mountain protected by a mile of solid rock from the world above. This is the home of Xenon, another Herculean effort in the same grand quest. Inside these subterranean sanctuaries, the level of obsession with purity and silence is almost beyond comprehension. The very air is scrubbed of radioactive radon gas. The materials used to build the detectors are painstakingly selected, measured for the faintest trace of natural radioactivity. Even the scientists themselves are a source of contamination. At the heart of these experiments lies a beautifully simple yet technically audacious idea. Imagine a large insulated vat filled with hundreds of kilograms of liquid xenon, cooled to a temperature of -100 degrees Celsius. This xenon must be purer than anything you have ever encountered. A single stray atom of the wrong kind could ruin years of work. Lining the top and bottom of this vessel are hundreds of ultra-sensitive light detectors called photomultiplier tubes, electronic eyes waiting patiently in the absolute dark. The theory is this: if a WIMP from the galactic halo happens to stream through the detector, there is a minuscule, almost zero chance that it will collide directly with the nucleus of a single xenon atom, like one billiard ball striking another in slow motion. This collision would be unimaginably gentle, but it would cause the xenon atom to recoil, and in doing so, it would emit a tiny fleeting burst of light and release a handful of electrons. The photomultiplier tubes are designed to catch this infinitesimal flash, this single photon of evidence. The liberated electrons, guided by an electric field, would drift to the top of the chamber, creating a second, slightly delayed signal. This double signature, a prompt flash of light from the collision, and a delayed signal from the electrons would be the golden ticket. It would be a unique, unambiguous fingerprint clearly distinguishable from the background noise of ordinary particles. It would be the moment humanity finally shook hands with the invisible universe. For years, these incredible machines listened. They sat in their profound, rocky silence, gathering data with a patience that bordered on the geologic. The teams of scientists, a global consortium of brilliant minds, watched the data streams refining their analyses, pushing the limits of their technology. They were sifting an ocean of silence for a single telltale sound. With each passing year, the experiments grew more sensitive. They went from Xenon 10 to Xenon 100, then Xenon 1T, and now Xenon NT, each iteration larger, quieter, and more powerful than the last. They were casting an ever finer net into the cosmic river, and they found nothing. Absolutely nothing. The silence from the depths of the Earth was deafening. The data plots where a cluster of events should have slowly appeared remained stubbornly, terrifyingly blank. The experiments were working perfectly. They were calibrated, they were shielded, they were performing exactly as designed. They were sensitive enough to see the faintest interactions from known particles, like neutrinos, proving their capabilities. But the promised signal, the gentle bump in the night from a dark matter particle, never came. Each new null result was not just a disappointment, it was a powerful scientific statement. It was like closing a door on a room you were sure contained something only to find it empty. With every new experimental run, physicists were able to rule out a vast range of possibilities for the WIMP's mass and its interaction strength. The WIMP miracle was beginning to look more like a mirage. The beautiful simple picture was fading, and a creeping anxiety began to permeate the field. The most promising candidate for the universe's missing mass was a no-show at its own party. While one community of scientists was listening for a whisper in the quietest places on Earth, another was trying a different, far more violent approach. They decided that if we couldn't wait for a dark matter to come to us, we would try to create it ourselves. Welcome to the Large Hadron Collider at CERN, on the border of France and Switzerland. This is the opposite of the deep underground labs. It is a temple of pure brute force. Here within a 27-kilometer ring of superconducting magnets, beams of protons are accelerated to 99. 999,991% the speed of light, carrying the energy of a freight train in a space smaller than a needlepoint. They are then smashed together in head-on collisions, recreating for a fleeting instant the unimaginable energies of the universe just moments after the Big Bang. The logic here is a beautiful application of Einstein's most famous equation E=mc². Energy can be converted into mass. By colliding particles with enough energy, you can create new heavier particles that may not have existed naturally since the dawn of time. The hope was that among the spectacular debris of these collisions, a shower of quarks, gluons, photons, and other exotic particles, we might forge WIMPs from pure energy. Of course, since these new dark matter particles would be invisible to the LHC's giant detectors, you couldn't see them directly. Instead, you would look for their shadow. Physicists would meticulously add up all the energy and momentum of the visible particles flying out from the collision point. If the numbers didn't balance, if some energy and momentum were mysteriously missing, it would be a smoking gun. It would imply that an invisible particle or a pair of them had been created and had flown away, carrying that missing energy with it, unimpeded by the giant magnets and calorimeters of the detector. It was an ingenious strategy, a hunt for a particle based on its conspicuous absence. For more than a decade, the LHC has performed quadrillions of these collisions. Its detectors the size of cathedrals and wired with more sensors than the human brain has. Neurons have sifted through petabytes of data enough to fill a stack of CDs that would reach the moon. They have famously found the Higgs boson, completing the standard model of particle physics in a moment of historic triumph. They have tested our understanding of the fundamental forces to exquisite precision. But in the search for dark matter, the result was heartbreakingly familiar. The energy books always balanced. The momentum ledgers were always clean. There was no missing energy, no shadow, no hint of a new invisible particle being forged in the LHC's fire. The cosmos's greatest machine, designed to reveal its deepest secrets, had joined the deep underground labs in their profound and unsettling silence. This compounding failure on two completely different experimental fronts plunged the field into a state of quiet crisis. The WIMP, for so long the undisputed frontrunner, the elegant solution everyone had bet on, was on life support. The parameter space where it could be hiding had shrunk so dramatically that many began to wonder if we had been chasing a ghost of our own creation all along. The lack of a signal was now more than just a lack of data, it was becoming data in itself. The data of absence. And in science, when your most cherished hypothesis is continuously contradicted by your best experiments, you must begin to consider the unthinkable. You must begin to ask the heretical questions. What if we're not just looking in the wrong place? What if we're not just using the wrong trap? What if there is no particle to find? This persistent, unnerving silence opened the door for ideas that had long been relegated to the fringes of cosmology. Chief among them was a radical, controversial, and deeply unsettling alternative known as MOND, or modified Newtonian dynamics. First proposed in the early 1980s by Israeli physicist Mordechai Milgram, MOND was a direct assault on the very foundations of the problem. It proposed that the galaxies were not full of invisible matter. Instead, it suggested that our understanding of gravity itself was wrong. Milgram pointed out that we have only ever tested Newton's and Einstein's laws of gravity within our solar system, where gravitational forces are relatively strong. What if he asked gravity behaves differently in the realms of extremely weak acceleration, like those found in the vast empty outer regions of a galaxy? MOND's central idea is a startlingly simple modification to Newton's famous law of universal gravitation. It posits that below a certain very low threshold of acceleration, gravity becomes slightly stronger than we expect. It doesn't die off quite as quickly with distance. This single small tweak, this subtle rewriting of a 300-year-old law, was able to explain the anomalous rotation of galaxies with breathtaking accuracy. It predicted the flat rotation curves that had so puzzled Vera Rubin without invoking a single particle of dark matter. The galaxy, according to MOND, doesn't need a halo of invisible mass to hold its outer stars in their orbits. The long arm of gravity itself is simply stronger out there. For decades, MOND was seen as a curiosity, a clever bit of curve fitting with little theoretical underpinning. But as the WIMP searches came up empty year after year, it gained a new and grudging respect. It wasn't just explaining away the data. In some cases, it was making successful predictions about the motions of stars in galaxies that were later confirmed by observation. Yet MOND is far from a perfect theory. While it works remarkably well for individual galaxies, it has struggled mightily to explain the observations on larger scales, such as the dynamics of entire galaxy, clusters the very evidence that first led Fritz Zwicky to propose dark matter. And most damningly, it has no convincing explanation for the patterns we see in the cosmic microwave background, the baby picture of the universe, which provides some of the strongest evidence for the existence of a non-baryonic cold, dark matter. This created a deep and fascinating schism in the heart of cosmology. On one side, the dark matter paradigm, a theory that preserved Einstein's theory of gravity, a law of physics we hold sacred, but required the existence of a mysterious unseen substance that makes up 85% of the universe's matter, a substance we have completely failed to find. On the other side, Esmond, a theory that eliminated the need for this phantom particle, but at the cost of modifying our most fundamental law of gravity, a change that seemed to work on some scales but failed on others. It was a profound impasse. An entire generation of physicists had dedicated their lives to the hunt building the most sophisticated detectors in human history, only to be met with an intransigent cosmos that refused to yield its secrets. The mystery of the missing mass was no longer a simple question of finding a new particle. It had deepened into a foundational crisis about the very nature of reality. Are we living in a universe filled with an invisible substance we can't touch? Or are we living in a universe governed by laws we don't fully understand? The silence from the Earth-bound experiments was a verdict our current path had reached a dead end. The frustration was palpable, the mystery more maddening than ever before. If we were to have any hope of breaking the deadlock, it was clear we needed a new window onto the problem. We needed a new way of seeing. We had to stop looking for a ghost in the machine here on Earth, and instead look for its footprints at the dawn of creation. The hunt had to leave the planet moving from the deepest mines to the highest perch, imaginable, searching for answers not in the present, but in the universe's most ancient past. And so, we waited. Trapped in a kind of cosmic paradox, we found ourselves inhabiting a universe whose fundamental blueprint we could not read. The evidence for an invisible majority was overwhelming, etched into the spin of every galaxy, and the clustering of every cosmic filament, yet the ghost itself remained elusive. Our most sensitive detectors, buried deep within the Earth, to escape the noise of our own world, heard only silence. Our most powerful theories, elegant and compelling, remained unproven. We had drawn the curtains on a magnificent stage, but could not see the primary actors. Humanity, for all its ambition, had hit a wall made of shadow. A new eye was needed. Not just a bigger eye, but a different kind of eye, one capable of looking not just further out into space, but deeper back into time, to the very beginning, to the moment the first actors took their places. On Christmas Day 2021, that eye began its journey. Rising from the jungles of French Guiana on a pillar of controlled fire, the James Webb Space Telescope was more than a successor to Hubble. It was a completely new form of perception. It was an instrument born of a profound and audacious gamble, a 25-year odyssey of invention delay and sheer human persistence. Folded like an intricate piece of technological origami to fit inside the nose cone of a rocket, its destiny lay not in a familiar orbit around Earth, but 1,000,000 miles away at a lonely gravitationally stable point in the quiet dark known as Lagrange Point 2. Out there, shielded from the blinding glare of the sun, the Earth, and even the Moon, it would begin a transformation. It would unfurl. Imagine a flower made of gold and glass blooming in the vacuum of space. 18 hexagonal mirrors, each polished to a perfection measured in atoms and coated in a microscopically thin layer of pure gold, unfolded to form a single colossal honeycomb 6.5 meters across. This golden web was not designed for vanity. Gold is exceptionally reflective of infrared light, the very medium in which the story of the early universe is written. Then the sun shield, a 5-layered kite the size of a tennis court deployed beneath it. Each layer, thinner than a human hair, would bleed off heat, creating a passive cryogenic cooler of breathtaking ingenuity. On the sun-facing side, the temperature would be hot enough to boil water, but in the shadow behind the fifth layer where the sensitive instruments lay, the telescope would achieve a staggering cold of -233 degrees Celsius. It had to be this cold for a simple and profound reason. To see the faint, ancient heat of the universe's dawn, the telescope itself had to be almost absolutely cold. It had to become a vessel of perfect silence, listening for the faintest thermal whispers carried across 13 billion years of expanding space. This ability to perceive the universe in infrared is the key to its power as a time machine. The cosmos you see is constantly expanding a truth discovered a century ago, and one that has shaped our entire understanding of reality. As the universe stretches, it also stretches the light travelling through it. Light from the very first stars and galaxies, which may have begun its journey, as brilliant blue or white ultraviolet light, has been stretched over its unimaginable voyage. Its wavelength has been elongated, pulled down the electromagnetic spectrum past red and deep into the invisible realm of the infrared. Hubble, for all its glory, was primarily an optical telescope. It could only catch the tail end of this ancient light. It was like trying to hear a symphony through a wall, catching only the faintest highest notes. JWST, by contrast, was built to hear the entire orchestra. It is an instrument tuned specifically to the frequency of creation, designed to witness the moment cosmic darkness first gave way to light. After 6 months of nerve-wracking commissioning, aligning the mirrors, testing the instruments, and holding the collective breath of the astronomical community, the first images arrived. And they were staggering. They were not just improvements on what we'd seen before. They were revelations, portals into a cosmos more intricate, more crowded, and more beautiful than we had ever dared to imagine. Nebulae where stars are born were resolved into three-dimensional landscapes of gas and dust, their inner sanctums pierced by Webb's infrared gaze. Dying stars were seen shedding their shells in exquisite ephemeral detail. But the true prize, the primary target for which this 20-year, $10 billion gamble was made, lay in the deep fields. These are the patches of sky that appear to the naked eye, and even to lesser telescopes, as utterly profoundly empty. JWST stared into these voids, its golden eye open, and unblinking for hours, then days, collecting photons that had been travelling since the universe was a mere toddler. What it sent back changed everything. The abyss was not empty. It was teeming with light. Thousands upon thousands of galaxies each, a smudge of ancient light littered the darkness. The sheer number was breathtaking, but it was the nature of these galaxies that sent a shockwave through the scientific world. Our theories, our meticulously crafted models of cosmic evolution, had painted a clear picture of the early universe. The first galaxies should have been small, clumpy, and irregular. They should have been wisps of primordial gas just beginning to coalesce, their first stars igniting in chaotic, disorganized bursts. They were supposed to be the cosmic seeds from which the great spirals and ellipticals of our modern universe would slowly, patiently grow over billions of years. It was a stately, gradual, and elegant model, and in an instant JWST's data declared that it was profoundly, fundamentally wrong. There in images capturing a time when the universe was only 300 to 400 million years old, a mere 2% of its current age were galaxies that had no right to exist. They were not small, clumpy, or chaotic. They were massive. Some appeared to contain stellar populations rivaling that of our own Milky Way today, a feat that should have taken billions, not millions of years to achieve. They were shockingly bright, blazing with the light of furious star formation, at rates that our models deemed physically impossible so early in time. Most unsettling of all, some of them were structured. We saw hints of galactic disks, of organized rotating systems of stars. These were not celestial infants. They looked more like cosmic teenagers, already mature and well-formed. It was like excavating a tiny primitive human settlement and finding a fully functional skyscraper in the middle of it. It simply did not make sense. The problem was one of time. The universe in its infancy was made almost exclusively of hydrogen and helium, the lightest and simplest elements forged in the Big Bang's initial flash. The heavier elements necessary for planets and life, the carbon, the oxygen, the iron, are manufactured in the hearts of stars and scattered through space when they die. Building a large galaxy requires time to form multiple generations of stars, time to enrich the cosmic gas with these heavier elements, and most importantly, time for gravity to do its slow, patient work of pulling all this material together. And time was the one thing these galaxies did not have. There simply hadn't been enough of it since the Big Bang for ordinary matter on its own to gather so quickly and form structures so grand. The speed of gravity acting only on the visible matter we could see was not fast enough. The universe appeared to be building its great cities far, far ahead of schedule. This impossible early galaxy problem, as it became known, created a crisis in cosmology. Did we have the age of the universe wrong? Was star formation wildly more efficient in the early cosmos than we ever imagined, or was there another unseen ingredient at play? And that is when the two great mysteries of modern astronomy, the puzzle of the impossible early galaxies and the enduring hunt for dark matter, began to converge in a breathtaking new synthesis. What if the reason these galaxies formed so fast was because they weren't starting from scratch? What if the ordinary matter, the familiar hydrogen, and helium was not the primary architect but merely the decorator, the first tenant moving into a vast pre-existing structure? What if the foundations of these cosmic cities had been laid long before the first stars ever ignited? This is where dark matter re-enters the story, not as an elusive particle to be caught in a lab, but as a cosmic phantom whose handiwork was now for the first time becoming visible. In our standard cosmological model, dark matter is the true cosmic sculptor. Because it does not interact with light or radiation, it was not pushed around by the intense energy of the early universe. While ordinary matter was being blasted and scattered by photons, dark matter immune to this pressure could begin clumping together under the gentle, relentless pull of its own gravity. It started to form vast invisible structures, a sort of cosmic scaffolding. It created deep wells in the fabric of space-time, immense invisible halos that would act as the gravitational anchors for everything to come. The theory predicted that this invisible framework should be in place very early on, providing the gravitational cradles in which the first galaxies would be born. According to this idea, the hydrogen and helium of the early universe were not pulling themselves together in a vacuum. Instead, they were flowing into these pre-existing dark matter basins like water, draining into the lowest points of a landscape. The process of galaxy formation was dramatically accelerated. The dark matter halos provided a massive gravitational head start, gathering the ordinary matter far more quickly and efficiently than it ever could on its own. Suddenly, the impossible galaxies seen by JWST made perfect, terrifying sense. They were so massive because they were built upon dark matter foundations that were 5 to 10 times more massive than the visible stars themselves. They were able to form so early because their skeletal frameworks were already in place, waiting for the visible universe to arrive. JWST wasn't just seeing the first galaxies, it was seeing the brilliant luminous paint on an invisible, gargantuan sculpture that had been shaping the universe from the very beginning. This was a stunning theoretical convergence, but Webb offered something even more profound, something far more direct than inference. It provided a way to weigh these ancient galaxies to measure their total mass, both visible and invisible. The key is one of Einstein's most beautiful predictions: gravity bends light. Any object with mass warps the space-time around it, and this curvature acts like a lens. Light from a more distant object passing by a massive galaxy on its way to us will have its path bent and magnified. This phenomenon, known as gravitational lensing, creates cosmic mirages, distorted, warped, and sometimes multiple images of the background object. The degree of this distortion is directly proportional to the mass of the foreground lens. It is a cosmic scale, allowing us to weigh a galaxy simply by observing how much it bends the light from behind it. And as astronomers sifted through the treasure trove of JWST's deep fields, they found them. Faint reddish arcs of light, the smeared and magnified images of even more distant galaxies, warped around the massive impossible galaxies in the foreground. For the first time, we could apply this cosmic scale to the infants of the universe, and the results were unambiguous. The mass required to create the lensing effects we were seeing was immense, far greater than the mass we could account for, by adding up all the stars and gas visible in the galaxies themselves. The numbers pointed to exactly the kind of massive invisible halos predicted by dark matter theory. Here at last was the smoking gun. Not a particle flicker in a terrestrial detector, but a direct gravitational fingerprint witnessed across 13 billion light-years. We were seeing the gravitational ghost in its cradle. This was a paradigm shift in the truest sense. For decades, the evidence for dark matter had been built on absence, on missing mass, on anomalous rotation speeds, on a universe that didn't add up. It was a story told by what we couldn't see. But JWST has transformed the narrative. It has allowed us to witness the positive, constructive influence of dark matter at the dawn of time. We are no longer just searching for a missing ingredient. We are observing the effects of the master recipe. We are seeing dark matter not as a problem to be solved, but as a fundamental creative force in the cosmos. It is the invisible loom upon which the entire tapestry of the visible universe has been woven. The galaxies we see, the stars that light our night sky, even the planet we stand on are all downstream consequences of this first shadowy act of creation. The James Webb Space Telescope was not built to find dark matter. It was built to find the first light. But in seeking the dawn of the visible universe, it appears to have stumbled upon the foundations of the invisible one. It has provided the first observational evidence that the universe we know is merely the luminous tip of a much larger, darker, and more mysterious iceberg. The implications are still being processed, debated, and modelled in supercomputers around the world. But one thing is clear: the silence from our earthbound detectors may not have been a sign of failure, but a hint that we were simply looking in the wrong place, or perhaps the wrong time. The definitive evidence for dark matter may not lie buried a mile beneath our feet, but 13 billion years in our past, waiting to be seen by a golden eye, floating in the cold and the dark. The ghost is finally beginning to take shape. Now the challenge is to understand its nature, and so the signal arrived, not with a thunderous clap, but as a quiet cascade of photons, a stream of ancient light captured and decoded in the silent hum of a server farm. For a breathtaking moment there was elation, the kind of pure, unadulterated thrill that comes from peering across 13 billion years and seeing something no human eye was ever meant to see. But that electrifying instant, that champagne-popping peak of discovery was fleeting. It was the sharp collective intake of breath before the plunge. Because what followed was not certainty, but a profound and unsettling silence, the kind that precedes a storm. Across the globe, as the data from Webb's first deep fields propagated through the scientific community, the initial wave of celebration quickly fractured, giving way to a seismic shock of intellectual vertigo. The numbers didn't just suggest a discovery, they screamed a paradox. These primordial galaxies, these ghostly infants from the cosmic dawn, were simply wrong. They were too bright, too massive, too structured. They were like finding the fossil of a fully formed eagle in Precambrian rock. The discovery intended to be a capstone for our understanding of cosmic evolution had instead become a lit match, tossed into the hallowed halls of cosmology. The first papers appeared online almost overnight, not as triumphant declarations, but as frantic, cautious reports, their titles laden with question marks. The emails flew, servers crashed under the demand for data access, and video calls crackled across time zones filled with the urgent hushed tones of theorists and observers trying to make sense of the impossible. Had Webb truly found the ghost in the machine, the dark matter halos that our theories had so long predicted, or had it found something else entirely, a flaw, not in the cosmos, but in ourselves, in the very blueprint we had so carefully constructed to explain everything we see? The elation had passed. The Inquisition had begun. The first line of defense for any scientific claim that threatens to overturn decades of established thought is skepticism. It is not a dismissal, but a rigorous systematic assault on the observation itself. Before you rewrite the laws of the universe, you must first prove beyond any shadow of a doubt that you are not being fooled. And light, especially light that has journeyed for over 95% of the age of time, is a master of deception. So the questions began, sharp and precise, aimed at the heart of the JWST data. Could the telescope itself be the source of the anomaly? Every instrument, no matter how perfect, has a ghost of its own, a subtle signature of noise or distortion. Scientists pored over the calibration files, searching for some minute overlooked flaw in the near-infrared camera, some systematic error that could be artificially inflating the brightness, and therefore the inferred mass of these distant galaxies. They checked and rechecked the complex algorithms that subtract the glow of our own solar system and galaxy, a process akin to trying to hear a whisper in a hurricane. Every calculation was scrutinized, every pixel put on trial. Yet the signal held. It was robust, clear, and terrifyingly real. If the instrument was true, perhaps the interpretation was false. Measuring the mass of a galaxy you cannot touch is one of the most difficult tasks in astronomy. You rely on proxies, on the subtle characteristics of light. The brightness of its stars tells you about the stellar mass, the ordinary visible matter we all know, but to weigh the dark matter, the invisible 85%, you must look for its gravitational influence. In the nearby universe, we can see this effect directly watching how a galaxy's gravity bends the light from objects behind it, a phenomenon called gravitational lensing. Or we can measure the speeds of its stars watching them orbit the galactic center, far faster than the visible mass alone would allow, held in place by the gravitational grip of an unseen halo. But for these nascent galaxies at the edge of time, such detailed measurements were impossible. Their light is too faint, their structures too compact. The teams had to rely on a more holistic method, comparing the total observed light and structure to complex computer simulations. These simulations, the product of decades of work, are our virtual universes, digital laboratories, where we can watch galaxies grow, according to the known laws of physics, with dark matter as the primary ingredient. The team's conclusion was stark. To explain the sheer brilliance and rapid assembly of these ancient galaxies, the simulations required an astonishing amount of dark matter, far more than our leading theories predicted should have been possible so early in cosmic history. The galaxies appeared to be living inside dark matter halos that were grotesquely oversized for their age, as if a newborn child had the skeleton of a full-grown adult. This is where the debate intensified, branching into a dozen different streams of intellectual combat. Could we be misjudging the age or nature of the stars themselves? In the primordial universe, the first stars were very different from our Sun. Forged from pure hydrogen and helium, the raw leftovers of the Big Bang, they were colossal, monstrous things, hundreds of times more massive than our own star. These celestial blowtorches burned fantastically bright and died explosively young. What if some argued these early galaxies were overwhelmingly populated by these first-generation population 3 stars? Their extreme luminosity could trick us. It could make a galaxy of relatively modest mass appear to be a cosmic titan, fooling us into thinking it needed a gigantic dark matter halo to hold it together. It was a plausible idea, a potential escape hatch, that would allow our cosmological model to survive intact. The problem was that even when models were adjusted to account for the most extreme populations of these super-bright, short-lived stars, they still fell short. They could not fully explain the sheer, unadulterated mass that Webb was seeing. The data still required a gravitational anchor, a cosmic scaffold far heavier and more established than seemed possible. The universe, it seemed, was not just building bright galaxies. It was building them on a foundation of darkness that had assembled itself with terrifying, unnatural speed. The escape hatch was closing. The walls of the established paradigm were beginning to feel less like a fortress and more like a cage. We were now face to face with the central pillar of modern cosmology, the lambda cold dark matter model, or lambda CDM. For more than 30 years, this has been our standard model of the universe. It is a story of cosmic architecture told in 2 parts. Lambda represents the dark energy that is accelerating the expansion of the universe, while cold dark matter is the protagonist of structure formation. In this grand narrative, dark matter is cold, meaning its particles move slowly, and it is non-interactive, meaning it feels gravity but nothing else. It is the perfect cosmic shepherd. In the moments after the Big Bang, tiny quantum fluctuations in the density of this dark matter began to grow. The slightly denser regions had slightly more gravity, and they began to pull in more dark matter, slowly, patiently, over hundreds of millions of years. This process is hierarchical. Small clumps form first, these tiny halos of dark matter, then merge and coalesce, growing into larger and larger structures, like raindrops trickling into streams, streams into rivers, and rivers into oceans. Ordinary matter, the hydrogen and helium gas of the early cosmos, is then drawn into these pre-existing gravitational wells. It is only inside these vast ghostly scaffolds of dark matter that the gas can become dense enough to collapse and ignite the first stars and galaxies. Lambda CDM is a beautiful, elegant theory, and for decades it has been astoundingly successful. It predicts the large-scale structure of the universe, the cosmic web of galaxy clusters and voids, with breathtaking accuracy. It explains the subtle temperature variations in the cosmic microwave background, the afterglow of the Big Bang. It has passed every test we have thrown at it, until now. The JWST observations were a direct assault on the very heart of this model, the principle of slow hierarchical growth. The standard model is a story of patience of structures built brick by painstaking brick over cosmic eons. Yet Webb had seemingly found fully formed cathedrals in an era when, according to the blueprint, only the foundation stones should have been laid. The galaxies were too massive, implying their dark matter halos had grown far too quickly. The model predicted a quiet, sparse cosmic nursery at this epoch. Webb had found a bustling, overcrowded metropolis lit by the glare of galaxies that had no right to exist. It was a temporal impossibility, a deep and troubling contradiction. The universe, at least in its infancy, appeared to be playing by a different set of rules. This dissonance sent theorists back to their blackboards, forcing them to reconsider the most fundamental part of the equation, the nature of dark matter itself. For so long we had characterized it by what it isn't. It isn't normal matter. It doesn't emit or reflect light. It doesn't interact with the electromagnetic force. This characterization of a cold, aloof, and gravitationally dominant substance was born of necessity. It was the simplest solution that fit the previous data. But what if this simplicity was a mask? What if dark matter was not so cold, not so aloof? The JWST results became a catalyst, breathing new life into alternative theories that had long lingered on the fringes of cosmology. Perhaps some proposed dark matter is not cold, but warm. A warm dark matter particle would move faster in the early universe. This higher velocity would resist the pull of gravity, effectively smoothing out the smallest, densest fluctuations. This would inhibit the formation of the very smallest dark matter halos, but under certain conditions it could potentially accelerate the formation of larger galaxy-sized ones. The model was complex and faced its own challenges as it struggled to reproduce the sheer number of small dwarf galaxies we see in the local universe today. But in the light of Webb's data, it was back on the table, a contender once more in the search for cosmic truth. An even more radical idea began to gain traction. What if dark matter interacts with itself? The standard, cold, dark matter model assumes the particles are like ghosts passing through each other without a flicker of recognition. But what if they were less like ghosts and more like billiard balls? This is the theory of self-interacting dark matter, or SIDM. In this scenario, dark matter particles can collide and scatter off one another. This new force, a kind of dark friction, would have profound consequences for the way halos form. In the hyper-dense environment of the early universe, these interactions could rapidly transfer energy, potentially allowing the central cores of dark matter halos to collapse and densify much, much faster than gravity alone would permit. A self-interacting dark matter halo would not have to wait for slow, hierarchical mergers. It could build its own dense core from within, providing a ready-made, super-dense gravitational crucible for a galaxy to form with astonishing speed. Suddenly, the impossible galaxies seen by Webb seemed a little less impossible. They might be the first observational evidence that dark matter is not just a passive gravitational scaffold, but an active dynamic substance with its own rich internal physics. The implications were staggering. It would mean that out there in the cosmic dark, an entire secret world of forces and interactions has been unfolding, a universe parallel to our own, whose existence we have only just begun to glimpse through its gravitational shadow play. The community found itself at a crossroads, a moment of profound and thrilling uncertainty. Every path forward was fraught with difficulty. To defend the standard model, one had to argue for an unknown and exotic astrophysics, a way for normal matter to form stars with an efficiency that bordered on the magical, somehow mimicking the effect of excess dark matter. It was an uncomfortable ad hoc solution that felt more like patching a leak than reinforcing a foundation. To accept the observations as evidence for new physics, one had to challenge a theory that had been the bedrock of cosmology for a generation. It meant opening a Pandora's box of possibilities for the nature of dark matter, each one more complex and harder to prove than the last. The debate was no longer about a single set of images from a new telescope. It was about the fundamental narrative of our cosmos. Was the story of our universe one of slow, predictable gravitational assembly, a symphony conducted by a simple cold and invisible hand, or was it something far stranger, a chaotic and violent drama driven by forces and substances whose true character remained utterly alien to us? The initial discovery had not provided an answer. It had instead revealed the breathtaking depth of our own ignorance. Webb had not just opened a new window onto the dawn of time, it had torn a hole in our map of the universe. And now, armed with this tantalizing, terrifying glimpse of the unknown, the real exploration was about to begin. We were standing on the shore of a new cosmic ocean, and the familiar stars we'd always used for navigation might no longer be enough to guide us. What had begun as a tantalizing whisper from the dawn of time was now amplifying into a roar that the entire scientific community was forced to confront. The initial discovery, those ghostly halos of influence surrounding the universe's first galaxies, had been both breathtaking and deeply unsettling. It was one thing to infer dark matter's presence from the graceful spin of a modern galaxy, or from the distorted light bending around a mature galactic cluster. It was another thing entirely to claim you had seen its handiwork shaping the very first specks of light to ever defy the cosmic darkness. The stakes were immense, and so understandably was the skepticism. Science, in its relentless and necessary caution, demanded more than a single stunning photograph. It demanded a case built not on one pillar of evidence, but on a foundation so broad and so deep that all other possibilities would simply collapse under its weight. The time for the solitary eureka moment was over. Now began the great work of confirmation, a meticulous global effort to transform a revolutionary claim into an undeniable truth. The first line of attack was not aimed at the sky, but at the silent humming cathedrals of computational power here on Earth. If we couldn't rewind time to watch the universe unfold, we would do the next best thing: we would build it ourselves. Inside the world's most advanced supercomputers, teams of astrophysicists began constructing digital cosmos, veritable universes in a box. These were not mere animations. They were staggeringly complex simulations, each one a parallel reality governed by the fundamental laws of physics. They began with the simplest of ingredients, the known conditions of the early universe, as measured from the cosmic microwave background, a smooth, hot, dense soup of hydrogen, helium, and a mysterious unseen substance. In some of these digital creations, that unseen substance was programmed to be dark matter, possessing its predicted properties, cold, slow-moving and interacting only through the immense patient force of gravity. In other simulations, a control group for the cosmos, it was left out entirely. These were the baryonic universes, worlds built only from the atoms we know and understand, the matter that makes up you, me, and every star we have ever seen. With the stage set and the laws of physics encoded, the simulators pressed run. For weeks, sometimes months, the machines churned through the calculations, tracking the gravitational attraction of quadrillions of virtual particles across 13 billion years of cosmic history. We watched mesmerized as these two different types of universes evolved. In the realities devoid of dark matter, gravity worked slowly, timidly. Without the massive invisible scaffolding to cling to ordinary matter, struggled to coalesce. The gas clouds remained diffuse, their self-gravity too weak to overcome their own internal pressure. The process of forming galaxies was lethargic, anemic. Stars flickered into life, yes, but they were few and far between. The structures that did manage to form were small, irregular, and took billions of years to assemble into anything resembling the galaxies we see today. When the simulators fast-forwarded to the epoch JWST was observing, just a few 100 million years after the Big Bang, these digital universes were still largely barren, their galaxies fragile and underdeveloped. They looked nothing like the brilliant, robust, and surprisingly mature galaxies that had stared back at us through Webb's golden eye. The simulation was a stark computational proof. A universe made only of what we can see is a universe that fails to build itself in time, Then we turned our attention to the other digital cosmos, the one seeded with the gravitational ghost of dark matter. Here the story was entirely different. From the very beginning, even before the first atoms had cooled enough to form, the dark matter was already at work. It was the silent architect, its immense gravity, creating a vast, invisible cosmic web, a network of dense filaments and massive nodes stretching across the expanding void. It carved out the gravitational valleys and basins into which ordinary matter would inevitably flow. The primordial hydrogen and helium, instead of drifting aimlessly, were now pulled by an irresistible force into these pre-existing dark matter halos. It was like pouring water onto a landscape already sculpted with riverbeds and lakes. The gas didn't have to blaze its own trail, it simply followed the paths of least resistance laid out for it by the dark matter. Within these deep gravitational wells, the gas compressed rapidly, reaching densities unimaginable in the other simulations. The fuse was lit. A firestorm of star formation erupted, turning these nascent halos into the brilliant beacons JWST had discovered. When the simulators paused at the same cosmic moment, the view was breathtakingly familiar. The galaxies that had formed were bright, compact, and teeming with young stars, their sizes and structures a near-perfect mirror of the real-world observations. The computer had not been told to draw these specific galaxies. It had been given only the laws of physics and the recipe of the universe. And the only recipe that worked, the only one that could reproduce the reality Webb had unveiled, was the one that included a massive dominant ingredient of dark matter. This was more than just a match. It was a powerful vindication. The simulations provided the crucial link, the why behind the what that Webb had seen. The telescope had shown us the results of surprisingly advanced galaxies in the cosmic dawn. The simulation showed us the process that such rapid early construction was impossible without a pre-existing dark matter framework. It was a pincer movement on the truth. From one side, direct observation. From the other, theoretical simulation. And where they met was the undeniable conclusion: dark matter was not just present in the early universe. It was the essential catalyst for its entire structural evolution. Without it, the universe as we know it would have been stillborn. Yet even this powerful convergence was not enough. To truly cement a consensus, the evidence had to come from more than one direction, more than one team, more than one set of distant galaxies. The universe had to provide corroborating witnesses. And as other scientific teams who'd been granted time on the revolutionary telescope began to publish their own findings, those witnesses started to step forward from the cosmic shadows. One group, focusing their gaze on a different, seemingly unremarkable patch of primeval sky, found another small collection of galaxies from the same epoch. They subjected their data to the same rigorous analysis, measuring the light, calculating the stellar mass, and charting the motion of the gas within. Their results, reached completely independently, were identical. These galaxies, too, were encased in massive halos of unseen matter, their visible components a mere 10% of their total gravitational footprint. Another team decided to look not at galaxies, but at the most distant quasars, the hyperluminous hearts of ancient galaxies powered by supermassive black holes. By studying the faint intervening wisps of hydrogen gas silhouetted against the quasar's brilliant light, a technique known as the Lyman alpha forest, they could map the distribution of matter on the largest of scales. Their map of the infant universe revealed a clumpy filamentary structure, a cosmic web far more developed and pronounced than it should have been if only ordinary matter existed. The gas was clearly tracing a far grander invisible structure beneath it. It was like seeing the network of streetlights at night and being able to infer the entire layout of a city's roads. Once again, the data screamed for dark matter. The observations were no longer isolated curiosities. They were becoming a pattern, a consistent signal repeated across the sky, seen through different methods by different eyes. The universe, it seemed, was telling the same story everywhere we looked. With the chorus of corroborating evidence growing louder, the focus returned to the original data, but now with an even finer-toothed comb. The linchpin of the entire argument rested on the accuracy of the mass and velocity measurements. Skeptics had rightly questioned whether astrophysicists were misinterpreting the light, perhaps mistaking a population of exotic, superluminous stars for a much larger number of normal ones, thereby inflating the mass estimates. This is where the sheer power of JWST's spectroscopic instruments, Particularly NearSpec came to the forefront, ready to dissect the galactic light with surgical precision. By splitting the faint ancient light into its constituent rainbow of colours, astronomers could read its chemical barcode. They weren't just seeing a smudge, they were seeing the specific signatures of elements like hydrogen, helium, and oxygen. The precise wavelengths of these spectral lines carried a treasure trove of information. Their redshift, the degree to which they were shifted towards the red end of the spectrum, confirmed the galaxy's immense distance and age with an accuracy that was previously unimaginable, silencing any debate that these might be closer, less massive objects masquerading as primordial giants. But the spectra held an even more critical secret. The width of these spectral lines revealed the internal motion of the gas clouds from which the stars were being born. A wider line meant the gas was churning more violently, a chaotic mix of clouds moving towards us and away from us at high speed, all held within the galaxy's gravitational grip. And the speeds were astonishing. The gas in these tiny infant galaxies was whipping around at hundreds of kilometers per second, a rotational velocity so high that the gravity of the visible stars and gas alone was utterly insufficient to hold it all together. Without some immense unseen source of mass, these primordial collections of stars should have torn themselves apart, their contents flung out into the void in a matter of moments. They should not exist. But there they were, stable and shining. It was the same fundamental problem seen in modern spiral galaxies, the one that had first launched the dark matter mystery decades ago, but now we were witnessing it at the very beginning of cosmic time. The spectral data was the smoking gun, a direct measurement of gravitational influence far exceeding what could be accounted for by the light. It transformed the dark matter halo from a necessary theoretical component into a measured physical requirement. Armed with this irrefutable kinematic evidence, the community could now systematically dismantle the alternative theories. The most prominent challenger, a framework known as modified Newtonian dynamics, or MOND, proposed that our understanding of gravity itself was flawed on galactic scales. MOND suggested that gravity becomes slightly stronger, at very low accelerations, eliminating the need for dark matter to explain the rotation of modern galaxies. It was an elegant if radical idea. But it was a theory fine-tuned to the universe of today, a universe of large, stable, well-ordered spiral galaxies. The infant universe was a different beast entirely. When theorists applied the MOND framework to the conditions JWST had observed, these small, compact, chaotically churning protogalaxies, the equations failed spectacularly. MOND simply could not generate the massive gravitational pull needed to contain the high-velocity gas seen in these primordial structures. It couldn't explain how they assembled so quickly, or why they were so robust. The theory broke down precisely at the moment it was needed most. The data from the cosmic dawn had provided a unique, brutal testing ground, and the alternative to dark matter had been found wanting. It was a decisive blow. The possibility that we had simply misunderstood gravity, a persistent doubt for decades, was now largely ruled out, at least in its current form. The problem wasn't with the law of gravity. The problem was that we had been blind to most of the matter it was acting upon. The effect on the scientific community was profound, a palpable shift that could be felt at conferences and in the tone of scientific papers. The initial wave of exciting but cautious reports gave way to a second wave of sober, rigorous analyses that confirmed and strengthened the original findings. At colloquiums, presentations that once might have been met with a barrage of skeptical questions were now met with nods of agreement and focused discussions about the implications. Former dissenters, the vital devil's advocates of the scientific process, began to publish papers acknowledging that the new JWST data presented a formidable, perhaps insurmountable challenge to their alternative models. This was not a surrender, but a testament to the integrity of the scientific method. It is a process that is not about being right, but about collectively getting it right. The evidence had grown so powerful, so multifaceted, with direct observation, computational simulation, independent corroboration, and the elimination of alternatives all pointing in the exact same direction, that it could no longer be reasonably denied. A consensus was not just forming, it was crystallizing into a hard scientific fact. The case was closed. We had found it. Not the particle itself, not the phantom that has eluded our detectors here on Earth, but something arguably more fundamental. We had seen its work, its undeniable gravitational signature etched into the very first blueprints of the cosmos. We had found its crucial role as the cosmic architect, the grand designer, the silent partner to gravity that sculpted the universe we inhabit. For decades, dark matter had been a necessary ghost, a phantom required to make our equations work for the modern universe. But now, thanks to this extraordinary new eye on the cosmos, we have finally tracked that ghost back to its origin. We have proven it was there from the very beginning, a foundational component of reality, as essential as hydrogen, as fundamental as light. This confirmation does more than just solve a long-standing cosmological problem. It deepens the mystery in the most tantalizing way. By validating its existence at the dawn of time and seeing precisely how it behaves, we have gathered our most important clues yet in the ongoing hunt for its true identity. We now know with more certainty than ever before that we live in a universe built upon an invisible foundation. And the urgent question, the one that now echoes louder than ever, has shifted from if it exists to the profound and thrilling challenge of what it is. And so the curtain of night is finally pulled back, not to reveal an empty stage, but an architecture of breathtaking, impossible scale. The images from Webb are not merely pictures, they are echoes of a verdict delivered 13 billion years ago. Here in the faint stretched light from the universe's infancy, we have seen the ghost. We have watched its gravitational hand guide the first embers of starlight into the magnificent structures that would one day become galaxies like our own. The long search born from the quiet persistence of a lone astronomer staring at the inexplicable spin of a galaxy has led us to this profound, unassailable truth. The missing mass was never truly missing. It was simply waiting for us to build an eye sharp enough to see the shapes it traced in the darkness. This moment feels like the crest of a great wave, a journey that has carried us across generations of scientific thought. You have to remember the sheer audacity of the initial claim, the intellectual courage it took to stand before the world and declare that everything we could see, every star, every galaxy, every wisp of glowing gas was but a sliver of reality. It was a proposition that bordered on the mystical, a cosmic heresy suggesting that the universe was governed by an invisible, untouchable presence. For decades, the evidence was subtle, a collection of curious anomalies. The stubborn refusal of galaxies to fly apart, the strange bending of light from distant quasars, the peculiar mottling of the cosmic microwave background radiation. Each was a clue, a breadcrumb dropped on a trail leading deep into an undiscovered country. They were whispers in the data spectral voices that most were inclined to dismiss as errors in our understanding of gravity as some yet unaccounted for conventional particle. But the whispers grew louder. With every new observatory, every more powerful simulation, the phantom's presence became more insistent. It became a necessary ingredient in our cosmic recipes, the one element without which the universe we observe simply could not exist. Yet it remained stubbornly indirect, an inference drawn from the behaviour of light and matter, not a direct observation. It was a shadow without a source, a gravitational fingerprint left by a culprit who had already fled the scene. We knew something was there, we could describe what it did, but we couldn't point to it and say, there, that is it. That is the chasm the James Webb Space Telescope has now bridged. It has transformed the abstract into the observable. By peering into the cradle of creation, into that nascent epoch, when the first galaxies were just beginning to coalesce, Webb has done something fundamentally new. It has not merely confirmed that dark matter exists in the modern universe, it has shown us that it was there from the very beginning. It was the primordial seed, the silent partner in the cosmic dance before the first star had even ignited. This is not just another piece of evidence, it is the cornerstone. It demonstrates that dark matter isn't a recent phenomenon or a quirk of galactic evolution. It is foundational. It is the original blueprint from which everything else was built. Think of it this way, for so long we have been like archaeologists trying to understand an ancient city by studying only its modern-day ruins, inferring the original layout from the remaining rubble. Now with Webb we have been handed the original architectural plans drawn up before a single stone was laid. We can see the invisible scaffolding that was erected, first the vast intricate network of dark matter filaments stretching across the void. We are witnessing in action how the first pockets of ordinary matter, the hydrogen and helium forged in the Big Bang, were irresistibly drawn into the deepest wells of this pre-existing gravitational structure. They fell like cosmic rain into these unseen valleys, pooling together, compressing under their own weight, until the pressure and temperature reached the critical point of ignition. The birth of the first stars was not a random scattered event. It was a direct consequence of the map laid out by dark matter. The locations of the first galaxies were not chosen by chance. They were predetermined by the densest nodes in this invisible cosmic web. Dark matter acted as the celestial shepherd, patiently herding the luminous material of the universe into brilliant shining flocks. This is the paradigm shift Webb has delivered. We no longer see dark matter as just an add-on, an extra gravitational glue holding things together. We now see it for what it truly is, the omnipresent silent sculptor of the cosmos. It is the artist and the galaxies, the stars, the planets, and ultimately we are the clay it has shaped over 13 billion years. This realization ripples outwards, touching every aspect of astrophysics and cosmology. Our models of galaxy formation, which have long included dark matter as a theoretical necessity, can now be calibrated against actual observations of its influence at the earliest times. We can test our theories in the ultimate laboratory, the nascent universe itself. By studying the size and distribution of those first galaxies, we can begin to deduce the properties of the dark matter that shaped them. Was it cold, moving slowly and clumping together easily to form dense compact seeds, or was it warm, moving faster and smearing out the initial structures leading to more diffuse primordial galaxies? The light from these ancient galaxies captured by Webb's golden mirror carries the answers. The subtle details in their structure, the way stars are clustered, the size of their gravitational halos, these are the clues that allow us to interrogate the fundamental nature of this elusive substance. We are moving beyond simply asking if dark matter exists, and we are now asking what it is. The astronomical detective story is beginning to merge with the world of particle physics as the clues gathered from the edge of space and time are handed over to scientists working in the deepest laboratories on Earth. For the first time, the search is no longer blind. For decades, physicists have been casting a wide net searching for a hypothetical particle that could explain the missing mass. They have built extraordinary instruments shielded from cosmic rays in deep underground mines, hoping to catch the fleeting whisper-faint signal of a dark matter particle bumping into one of their detectors. Experiments using vast vats of supercooled liquid xenon or arrays of hyper-pure germanium crystals have been listening in profound silence, waiting for a single anomalous flash of light, a single vibration that could betray the particle's passage. Others have been searching for the products of dark matter annihilation, looking for an excess of gamma rays or antimatter coming from the dense centre of our own galaxy, where the phantom substance should be most concentrated. These experiments were guided by theory, by elegant mathematical models proposing candidates like WIMPs, weakly interacting massive particles, or the much lighter wave-like axions. But without observational constraints, the search space was immense. It was like looking for a single specific grain of sand on all the beaches of the world. Now the game has changed. The observations from Webb act as a cosmic filter, narrowing the possibilities and focusing the search. The data from those primordial galaxies provides tangible properties, a profile of the suspect. It tells us about the mass, the temperature, the clustering behaviour of the dark matter particle. This new information is a treasure map for particle physicists. It allows them to fine-tune their experiments, to recalibrate their detectors, to look in the most promising energy ranges. It helps them decide which theoretical models are worth pursuing and which can be discarded as inconsistent with the new cosmic reality. The quest to identify dark matter is no longer two separate fields, astronomy and particle physics working in parallel. It is now a single unified endeavour, a pincer movement on the greatest mystery in science. The view from the top of the mountain looking back to the dawn of time is now guiding the search in the deepest caverns of the Earth. One hand is pointing at the cosmic architecture while the other is preparing the trap to catch the architect. And the journey is far from over. Webb has opened the door, but we have only taken the first steps inside. The next generation of observatories is already being designed and engineered to build on Webb's legacy. Telescopes like the Nancy Grace Roman Space Telescope will survey vast swathes of the sky, mapping the distribution of dark matter across cosmic history with unprecedented precision. It will create a three-dimensional map of this invisible scaffold on an enormous scale, revealing its structure, not just in the distant past, but charting its evolution over billions of years. Ground-based observatories with colossal mirrors capable of gathering immense amounts of light will perform spectroscopic surveys of millions of galaxies, tracing their movements to infer the gravitational landscape with stunning detail. Each new instrument will add another layer to our understanding, another piece to the puzzle. We will chart the tendrils of the cosmic web in exquisite detail. We will watch how dark matter halos grow and merge over cosmic time. We will test the very limits of our theories, searching for any deviation, any subtle effect that could point us toward a final theory of its nature. We stand on the cusp of an era where dark matter is no longer a placeholder in our equations, but a tangible, mappable component of the cosmos as real and as fundamental as the stars themselves. So we find ourselves here at the end of one journey and the beginning of another. We have followed a trail of gravitational breadcrumbs from the outskirts of our neighbouring Andromeda galaxy all the way back to the flickering light of the first stellar nurseries. We have seen the hand of an invisible sculptor at work shaping the universe we call home. We have learned that the cosmos is grander, stranger and more mysterious than we ever dared to imagine. The stars we see on the clearest night are but the luminous foam on a deep, dark, invisible ocean. The confirmation of dark matter's ancient and vital role is more than just a scientific victory. It is a profound lesson in cosmic humility. It is a reminder that our senses perceive only a fragile slice of reality. It tells us that for all our progress, for all our knowledge, we have been living in a world where 5/6 of its substance has remained completely unknown to us. It is a universe filled with a form of matter that does not shine, that does not burn, that does not reflect or absorb light. A substance that flows through our bodies, through the earth, through the very fabric of space as effortlessly and as silently as a ghost. The final revelation, the unmasking of the particle itself, may still be years or even decades away. It will require new technologies, new ideas, and perhaps another stroke of genius from a new generation of explorers. But for the first time, the path forward is illuminated. The search is no longer a shot in the dark. It is a focused, data-driven quest. And when that day comes, when we can finally name the particle that has held the universe together for 13 billion years, it will mark a turning point in human history. It will be the completion of the census of the universe, the final chapter in the story of what our cosmos is made of. Until then, we look up at the night sky with new eyes. We see not just points of light, but the visible markers of a grand hidden architecture. We see the silent gravitational scaffolding that makes it all possible. The universe has shared one of its deepest secrets, a secret held since the dawn of time. And in doing so, it has invited us to ask the next question, to push deeper into the mystery, to continue the greatest adventure of all, the quest to understand our place within the grand, dark and beautiful expanse of everything.